Okay, if we want to understand the evolution of mate choice, then it's a prerequisite that we understand what it is that the choosy sex, which I shall assume is the female purpose of this course, what is it that they actually are choosy about? Now, there are two types of preference which I think are extremely important in this regard. The first is directional preference, which is shown in this slide. On this axis we have the male trait value, and here we have female preference. So in this case, males that have larger values are preferred by the female, and a simple preference equation for that might be simply Bx. The other type of preference is stabilizing preference, where we have a female with a particular preference, and that preference might vary over the population. So I'm going to focus on the mean female preference, and so she prefers a particular preference, a particular trait value. As the males deviate from that trait value, her preference goes down. So a simple example of that would be if her preference was equal to the absolute value of the difference between her preferred value and the actual male trait value. So what we want to be able to do then is to estimate these two different types of preferences using some particular sort of experiment. And there are both no choice and choice experiments. I'm going to focus upon choice experiments. This is a typical choice experiment. We present a female with a choice of two signals. We looked at 41 different studies, and the mean number of males used in the study was 2.4 and a median of 2. So the experiment for each trial consists of two signals and one female, and the dependent variable is a measure of the female preference for each signal. The independent variable is either two artificially generated signals which suffer from a problem that they have a potentially, they don't have the right background that a typical signal might have, so that's one problem with those. Or maybe two distinct males, a bright red male and a dull male. The problem with this type of experiment is it cannot measure stabilizing preference. It can only measure the possibility of a directional preference for those particular two extremes. So an alternate experiment is one where we use two males, but these are selected at random from the population and presented with the female. Again, our dependent variable is a measure of the female preference for each male. The independent variable is some measurable trait, such as its color, such as number of chirp rate, if it happens to be a cricket, something like that. So now we want algorithms then to ask, do we have directional selection? Do we have stabilizing selection? Well, first of all, we define a relative preference value, and this is the preference of the female for the focal male, and the focal male is arbitrary. It could be either one of those two males. And the preference value might be, for example, the number of trips that the female makes towards the focal male. And we divide that by the sum of all of the trips made by that female. We then define a relative trait value, which is the preference of for the focal male based upon the trait value. So in this case then, it would be the value of the focal male divided by the sum of both the focal and the non-focal male. And the example here is the chirp rate of the focal male divided by the sum of those two. What we then simply do is to regress the relative preference on the relative trait value. And we would expect then, if it's directional selection, to get a significant relationship, which might be linear, it might not be linear, we'll just do a transformation if it isn't. So that's a very simple approach for that. Stabilizing preference is a little bit more tricky. We still have the same relative preference value, but now the relative trait value is defined somewhat differently. We take the absolute value between the trait value of the focal male, we subtract that from the mean preference of the females in the population. At the moment, we're assuming we know that. So we take that and we divide it by the sum of those two absolute values. And to make the regression positive, we take 1 minus that. So for example, if this focal male is exactly at mu, this would be 0, and the preference would be then 1. We do then the same thing that we did before. We regress the relative preference on a relative trait value. The problem we have, of course, is that we actually don't know what this value actually is. So what we do now is we vary mu over a range, and we fit this equation, or fit a regression to this line for each value of mu, and we get a correlation between those two. And so this then is, on this axis we have the trial value of all of those mu's. Here we have then the correlation squared, and what we expect if we've got stabilizing selection is that as we move away from that value, the R-square value should drop off. So if we find a value that is greater than the significant value for a regression, so this is just the value of R that would be significant given that number of data points squared, if it is significantly above that, or sorry, if it is above that and is concave, then we have demonstrated that there is stabilizing preference. However, what we now want to do is actually estimate what that mean value is and what the standard error is. So to do that, we use the bootstrap. So we've got n data points to start with. We select n trials at random with replacement from the original data set. We use the previous algorithm to estimate the mean female preference, so that would be mu hat 1 in this case. We repeat this step 1,000 times to generate 1,000 bootstrap replicas. The bootstrap estimate then is simply the mean of all of those replicas. And the standard error of the estimate is the standard deviation of those bootstraps. We've demonstrated that this works using simulation modeling, and I won't go into that. What I want to do is to show you three examples of how this process actually works. These examples are taken from this choice experiment using crickets, and what we have is a female, a male in a container here, and a male in a container here. The female cannot interact with the male because they're in these separate containers, but they can nevertheless hear the male. We have motion detectors on either side, so in this experiment run for 24 hours, we can know how often the male calls, what components of the call using these recorders are, and also how many times does the female pass the motion detector to get a measure of her preference. The three traits I'm going to talk about today are the carrier frequency of the call, the duration of calling, and the chirp rate. So the first one then is the carrier frequency of the male calling song. This is then the test for directional selection. On this axis we have the preference for the focal male based on its trait values, and the preference for the focal male based upon the relative number of trips the female made to that male. What you can see here, no, I should say there are 93 observations in this experiment. In this case, you can see there's absolutely no relationship between this preference and the relative preference and the relative trait values. Similarly, if we look at in this case I put the signed R-squared because in fact for non-significant values the slopes might actually appear to be negative, so I've actually signed this. And this is the 5% significance level, so it has to go above that in order to demonstrate stabilizing selection. These are the actual estimates, and you can see that they lie well below the significance level, so there's no evidence of stabilizing preference. This is actually the bootstrap distribution, the bootstrap mean and the population mean, but they're not actually different. This is an example where we have directional selection, directional preference rather, which should result, of course, in selection, directional selection. And this is the duration of the mail calling song, so the number of minutes called in a 24-hour period. And here we see a highly significant correlation between the preference for that vocal mail and the relative trait value. If we look at the stabilizing preference graph, what we find here is that in fact it exceeds the 5% significance level, but it never goes below it. And this is what you expect, shown from the simulation models, when you've got directional preference. Finally, we have a case where we have both directional preference and stabilizing preference acting together. And this is the chirp rate of the male calling song of the cricket. And here you can see there is a highly significant positive correlation, so females prefer males that have relatively high chirp rates. On the other hand, when we do the stabilizing preference test, we find that it's not significant here, not significant. It goes above the significance level and then drops below the significance level at the higher values. This shows the bootstrap distribution. This is the bootstrap mean and the population mean. So females are preferring males that are higher than average, but not to the point where they're at this level. So we have both the stabilizing and directional preference operating at the same time. So the proposed method makes use of data from a simple binary choice experiment. It uses randomly selected males to test for the presence of directional and stabilizing preference. Our simulation modeling has shown that the method is statistically satisfactory both for type 1 and type 2 errors, and is robust to the female preference model. And this method, as we've shown, successfully detects directional and stabilizing preference of male sun crickets for the call songs. We can extend this method to include multiple traits by either using PCs, using multiple regression, or some other way of aggregating trait values. And the method will be available as, hopefully, in the near future as an R add-on. Okay, thank you.
Stabilizing preference estimated marginal to the directional preference? Are they in the model at the same time, or are they separate?
They're in the model at the same time. And again, the simulation model has shown you can do it, although when you've got them both active, the significance level for directional preference should be set at the 0.01 level, not the 0.05 level.